Hello all, welcome to this video. Today we will discuss Transmission Control Protocol, or which is also called as TCP. We all know that TCP sits on the fourth layer, that is the transport layer in a TCP IP suite. And we will have come across many port numbers like 20, which is used for FTP, port number 80, which is used for HTTP, and port number 67, which is used for DHCP. Right now, what we have to understand here is that why TCP came into existence in the first place, right? And as network engineers, why is it important for us to know TCP? Right, so these things we will be discussing today, and we will also discuss its header formats and its fields in the header formats, and how those fields work when they are communicating with other transport layer protocols like TCP on sitting on the other device. So answering the first question as to why do we need a TCP protocol, right, which is on the transport layer, or instead of saying TCP, why do we need a transport layer in the first place, right? So let us take an example where we have a TCP IP suite which does not have a transport layer. So just imagine that we do not have these two layers sitting on device A and device B, right? Now, let us consider that the IP address of device A is 1.1.1.1, and the IP address of device B is 2.2.2.2, right? Now, A wants to send some message to B. Let's imagine that this A and B device are two mobile phones, and the application that a user is running on them is a WhatsApp. For example, they both are running a WhatsApp, right? They are chatting with each other. Now, let's say that A sent a message saying, "How are you?" Right? How are you? So this message has to reach the mobile user B, right? Now, if there is no transport layer, right, the message "How are you" is encapsulated, right? And it is encapsulated by the network layer, right? And it is sent across the network. So let's imagine that we have multiple routers sitting on the network. Okay. Now, this message has to reach B via this network. And there is a high chance that not all these message that "How are you," right? It may be sent as one single message, it may be sent as multiple messages, right? And there is a high chance that not all these messages travel through the same path. For example, let's say how. Let us consider how as one single message, R as one single message, and U and question mark as one single message. So there is a chance that how may use this path, right? R may use this path, and U will use this path. And there is also a high chance that one of them, let's say R, right? This message, "How are you?" In this message, R message gets dropped at this router. So what would be received? It would just receive the message as "How you," which it does not make any sense. Correct. So how will B tell A that your message is incomplete, or how will A know that the message is incomplete and I need to send the message R once again? So in network layer, there is no such field which tells either of the applications or sitting on the devices to let them be aware of a missing information in the traffic. That is why transport layer came into existence. The developers of transport layer, they knew that network layer does not have the capability to understand that the message or the data that it has received has missing information, and hence transport layer helps us with that, right? So that is why TCP came, not TCP, transport layer came into an existence. TCP is just one of the protocols that is used in transport layer. The other commonly used protocol in TCP in the transport layer is UDP, user datagram protocol. Now, as network engineers, why are we supposed to know TCP? Okay, now we network engineers are experts in data link layer and network layer protocols, right? In data link layer, you have spanning tree protocols, you have VLANs, then you have HSRP protocols, etc. And in the network layer, we have OSPF, BGP, ISIS, EIGRP, etc. All these protocols, they run on network layer, right? And as network engineers, we are experts, or we tend to learn more and more about data link layer and network layer, right? Then we have developers, right? We have admins, right? And we have many other software engineers who work on application layer protocol, like they create HTML pages, web pages, all those things, right? And they work with application layer protocol, right? So if there is any problem with your web browsing, if there is any problem with the website, if there is any problem with the coding behind the a software that is running on your device, the application layer engineer takes care of it, right? If there is a problem with network, if there is a problem with delay, if there is problem with VLANs, if there is problem with routing, right? All those things can be taken care by the network engineers who work on layer 3 and layer 2, right? But if there is any problem where the message or the data has not reached completely, right? For example, as I had in see as we had seen in our previous example, where how are you is sent from A to B, right? So it did not reach the B device properly, right? So as a network engineer, we will check if the routing is proper or not, right? So I would check that the routing is fine, right? The message can go from R1 to R2, right? And to R3, or whatever best path or is chosen by the routing protocol that we are using, right? We checked everything is fine. There is no problem with routing protocol. There is no problem with uh, 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 the routing table not being updated, etc. All those network layer troubleshooting we have done, and we say that it's okay, I'm fine. The network layer troubleshooting is all good. There is no problem with routing, right? Now the application layer engineer, he would check all his sites troubleshooting, right? And he would say it's I'm sending all the messages, I'm fine, right? So there is something missing in between, right? That no one actually addresses. Neither the network layer engineer or the application layer engineer take the responsibility of. That is transport layer. And hence, as network engineers, I feel that it is our responsibility to take the issues in the transport layer and address them. And knowing transport layer transmission control protocol of the transport layer is very easy. Troubleshooting TCPs are very easy once we know what are the fields inside a TCP header and how do they work. If we know that, learning TCP and troubleshooting TCP is very easy as network engineers. So moving on, right? So here the most common protocol used in the transport layer is TCP, and on the screen we can see that we have a header format of a TCP, transmission control protocol, right? So you have the length of this TCP header is 32 bits, right? Starting from here till here, the length is 32 bits, right? And you have a 16-bit port address, 16 bits destination port address, 32-bit sequence number, acknowledgement number, then you have a header length, reserved bits, and all these flags: urgent, acknowledgement, push, reset, syn, finish. All these are 1-bit flags, and you have a 16-bit window size, 16-bit checksum, urgent pointer, etc. Now, what we are going to do is we are going to go one by one about these headers and how, what kind of role and how important role do they play in this transmission control protocol. So source port number and a destination port number, right? As we have seen in layer 2, we have source MAC address and a destination MAC address. In the IP header, we have a source IP and a destination IP. Similarly, in your TCP, we have a source port address and a destination port address. Now, they are very similar to all the layer 3 and layer 2 addresses, where the destination port address is a very commonly used port address, as we have seen earlier, like port number 80. It is a very common port number for HTTP, right? And we have 20 and 21 for file transfer protocol, port number 67 for DHCP, right? So these are all destination port numbers, right? So they are fixed destination port numbers. Now, how are these destination port numbers different from an IP address, right? Now, consider that you your company has a name, right? Now, let's say that you are working in a company called 10.10.10.10. This is your company name, right? Now you are an employee of that particular company. So someone comes to meet you at 10.10.10.10. So how will that person identify you that he needs to meet you at 10.10.10.10, right? So you will have a port address or a port number. That port number is a very famous port number. It can be anything, any one of these, right? So for example, it is port number 80. So your port number is 80 and your name is ABC, right? So anyone who is coming at 10.10.10.10 and wants to talk to ABC can use the port number 80 to reach out to you. This is the work of a port number. So at a particular address, for example, right, a port number 80 is used for web browsing. So let's, for example, on Google, there are so many links, there are so many uh, links, and there are so many information. So for example, this is Google's address 10.10.10.10. Now you want to use a particular application of Google, right? So you say that, or you want to use, or you want to click on a particular link. That link will have something, right? That link is actually related to HTML, HTTPS, etc. We are not going to digress from that, but 10.10.10.10 is the address, and AT is the application that you want to use. All right. Now, source port address is actually a random address that is created. Okay, that is randomly created by the originator or creator of this TCP header, right? That particular source port address is random, so it is 2 power 16, right? So it is 65,536, so 35, right? So from 0 to 65,535, 0 is not actually used, so it should be 1. 1 to 65,535 is the number of port source port addresses that you can create, and the originator of the TCP header generates this source port address randomly. All right. Now, moving on to the next header here, that is the sequence number. Right. Now, sequence number and acknowledgement number are the two most important factors due to which we call TCP a connection oriented protocol. What is connection oriented protocol? Meaning that it is reliable. It's reliable in a way that no information is missed from point A to point B. That is called as reliability. Now, how do these sequence number and acknowledgement number work? In a very short way, or in a very uh, quick way that I can explain is, so you have device A and device B, right? Or you can call them as person A and person B. Now, for example, person A says hello to person B, right? So B hears this hello and he responds back with his hello, right? So the first hello that is sent from A to B is called as a synchronization message, right? Synchronization message. And the response from B to A that is sent is called as an acknowledgement, right? So all these information that is communicated between A and B will have a sequence number, right? So based on the sequence numbers, A and B will come to know which message is missed or which message has to be received next. So every message that is communicated between A and B will have a sequence number. For each and every sequence number, there will be an acknowledgement number that is received from the other side. We will discuss more on this later when we get into details of how sequence number and the bytes of information and the acknowledgement number, they play an important role. We will discuss these later, right? Now, header length. This header length is actually 4 bits long, right? So this header length tells that what is the size of this TCP header. So how many rows do we have? We have 1, 2, 3, 4, 5, right? Except this option and padding, we have 5 rows, right? And the length of one row is 32 bits, right? So that makes it 32 into 5, which makes it 160 bits. If we convert them into bytes, we have 20 bytes. So the minimum size of a TCP header is 20 bytes, and the maximum that it can go to is 60 bytes. Right now, there is an important interview question that they usually ask: if the minimum size of the TCP header is 20 bytes, right, and if the maximum size of the TCP header is 60 bytes, this 4-bit header, right, If it is 4-bit header, we have 1 1 1 1, right? So if we convert it into if we convert it into a decimal format, this would be 15, right? So this is 15 bytes, right? How will a 15 bytes header denote the header length whose size is 60 bytes? This is a very important interview question that they ask. And here is where people get confused and they do not know the answer. So, as I had mentioned, the minimum size of the TCP header is 20 bytes, right? Now, we have a header length of 4 bits. So, 0, 0, 0, 0, right? Now, to denote the size of a header length, we use a scaling factor. We use a scaling factor which is 4, right? Which is 4. So any number that is um, denoted in the header length is multiplied by this scaling factor. So if 20 bytes is the minimum size of the TCP header, right? So the header length that is denoted in the header field will be 0101, which in decimal is 5. And if we multiply it with 4, we get 20. So this is how the minimum size of the header length is denoted in the header field. It is 0101. So automatically the device multiplies it with a scaling factor of 4 and denotes the minimum size as 20 bytes. So if it goes to the maximum, that is 1111, which in decimal is 15, and if we multiply it with a scaling factor of 4, we get it as 60 bytes. So the device can understand that if the header length field has all ones, it has to multiply it with 4 so that it gets a value of 60 bytes. And this is how all the length of the header, TCP header, is calculated. Okay. So the minimum size is 20 bytes, and below this, it cannot be seen in the header length. Below this value, it cannot be seen in the header length. Now coming back to the header once again. Oops. Let me erase all this. So the next field that we will see is reserved bits, which is actually a 6 bits field, and we will discuss this later. The other 1 bit fields, that is urgent field, that is the urgent field, acknowledgement field, push, reset, syn, and fin. Okay, these are called as flags. These are called as flags. Okay, so when there is a data transfer between A and B using TCP, all these flags come into play one by one. It depends on the kind of information that is being transferred from A to B, and based on that particular information, these flags are set. So since these are 1 bit flag, so the value can either be 0 or 1. So if an acknowledgement is being received, as I had told earlier, an acknowledgement is an acknowledgement received after a SYN is sent from A to B, right? So acknowledgement is a response to a data that has been received from one party to the other party. So if an acknowledgement is being sent, so the acknowledgement bit will be set as 1, right? If a synchronization message is sent, right? The very first message in a TCP handshake is called as SYN message or synchronization message. If that is being sent, SYN bit is set as 1, right? So we will discuss all these flags later one by one, right? Then we have something called as window size. Window size can be thought as a buffer, right? What is a buffer? It means a space, an empty space, right? The amount of space that this particular container can be filled is called as buffer. So the sender and the receiver in a TCP protocol have a buffer size, right? And they tell each other that that amount of buffer size they have for the data to be received. Let me explain this once again. So let's say that you have device A and device B, right? Hypothetically, let's say that A says to B that, hi B, I have 200 MB of space with me. That means that it is saying to B that I can receive an a data whose size is 200 MB, right? Similarly, B can say that I have 500 MB of space with me, meaning that A can send a data of size 500 MB. It is not necessary that it has to send all these 500 MB in one go. It can send in multiple segments, right? So let's say that A says I have 200 MB of storage space, right? Let's call that as buffer. I have 200 MB of buffer, which is received by B. Similarly, B says I have 500 MB. So as the data that is being transferred from A to B, right? So let's imagine that A sent a data of 10 MB, 10 MB to B, right? So B has received 10 MB of data. So now instead of 500 MB of space, it will say that I have 490 MB of space, right? I have 490 MB of data, right? Similarly, if B sends 10 MB of data to A, right, the buffer space for A would be 190 MB, right? So buffer is nothing but buffer or window size here means that the amount of space or amount of buffer that is left on the device to accept that amount of data. If this buffer or if this window size gets filled completely, the device or the party here, A or B, cannot receive data. It cannot receive data. It has to empty that window size or that buffer or that storage, whatever you call it in a layman's word, but it has to empty that space, then only it can receive extra data here. That is the work of window size. Window size tells the other party the amount of storage or buffer left for the extra data to receive. Now, checksum and urgent pointer, right? So checksum, as we have already seen in the layer 2 and layer 3 header, is it checks the integrity of the data that is being received, right? So there is a checksum calculation that is done on A side when this TCP header is sent. The same checksum calculation is done on B side, right? If the checksum value matches on both ends, both the party know that the information or the data that is received is uncorrupted. It is completely safe, right? Now, urgent pointer. This is another important question that they usually ask. Urgent and urgent pointer. The urgent here meaning the urgent bit that we can see here. The common question that is usually asked in the interview is that what is the difference between an urgent bit and the urgent pointer, right? So let us understand that. Let me erase this drawing here first. So TCP is actually a continuous stream of data that is being sent across in segments, right? So let's imagine that there's a, uh tube. Okay, there's a tube between these two layers here, right? So the data is actually being sent across in a continuous stream of bytes, right? Each information in TCP is bytes. Okay, now the question that they ask in interview is what is the difference between the urgent bit and the urgent pointer, right? What is the difference between these two? So in TCP, usually the data is sent in segments, right? And these segments contains multiple bytes of information. They have multiple bytes of information. So let us imagine that this is a segment, right? And all these boxes are one bytes, right? So they are sent. This whole segment is sent across this particular pipe. Just imagine this visually, and this is a very hypothetical situation that I'm giving you, right? But just for visual understanding, let's imagine that this segment with multiple bytes is sent across this pipe, right? Now you uh, have an application running on A and B here, right? Now when is this urgent bit set? Now let's say that this application layer says that I have something urgent or some a priority information that I need to send it across to B, right? What can it do? Usually, all these bytes, or you can call it, or this segment is actually filled in a sequential manner, right? In a sequential manner. So if let's say that it already has this segment already has 1 2 3 4 bytes already filled, right, to be sent across this particular pipe here, right? Now the application layer said that I have an urgent byte that I need to send, right? So what it does is in the TCP header, right, in the TCP header it sets the urgent bit as 1 and it sends it to the transport layer. Now what transport layer does is it shifts all these bytes. It does not shift, it places this urgent byte. It places this urgent byte in the first, so that it is first part of the segment or first byte of the segment, right? So that it is sent first across this particular pipe, right? When the B device receives this particular segment and sees the urgent bit set as 1, it knows that the segment that it has received, the first byte, has some urgent information and it needs to send it to the application layer, right? So this is what urgent bit does. It places that particular urgent or priority byte into the first place in the segment and sends it across instead of uh, instead of placing it in a sequential manner, right? The B side, the moment it sees the urgent bit as 1, it takes it out and sends it to the application layer. Now, the urgent pointer, what is the work of the urgent pointer? Urgent pointer points, urgent pointer points to the place where that particular urgent byte is sitting. Urgent byte, sorry, the urgent pointer points at the segment and says that this is where the urgent byte is sitting. It helps the receiving application layer to read that particular urgent byte and send it to the application layer. This is the difference between urgent and urgent pointer. Urgent bit sets the urgent bit as 1, places the byte in the first of the segment and sends it across. Urgent pointer points where this particular urgent byte is sitting in the segment, and it helps for the receiver application layer to read it. Now, coming to the most important uh, factor or feature with which the TCP communicates between end devices is the buffer or the window size, right? So imagine that imagine that a buffer is actually a chamber, right? Like this, that is drawn here, a chamber, right? And this particular chamber is present on the sender side as well as on the receiver side. Okay, now the application layer on the sender side, right? The application layer on the sender side keeps sending information, right? And the transport layer on the receiver side keeps sending information to the application layer. Okay, so the application layer keeps sending information to the transport layer here, and on the receiver side, the transport layer keeps sending information to the application layer. Okay, since it is a continuous stream of data or bytes, right? These chambers, as you see here, keeps getting filled and keep getting filled, keep getting emptied also, right? Now, on the sender side, you can consider this buffer or this chamber in as chambers, and it has three chambers, right? So one chamber, as you see here, I have marked it with blue, right? So the blue chamber, right? The blue chamber contains data that are sent, data that are already sent, right? Meaning that sender has sent that particular bytes or data to the receiver side, and it is waiting for an acknowledgement, right? It is waiting for an acknowledgement. The moment it gets acknowledged, these chambers in this buffer will get empty. They will be emptied or they will be vacant, right? Now, the orange ones. The orange ones are the data which orange are the data that are waiting to be sent, right? That are waiting to be sent, right? So the moment the segment is full, right, or the segment is full, it will be sent. It will be sent across, and they will get converted into blue, meaning that they will also be waiting for the acknowledgement to be received from the receiver. Okay, so sender has three chambers. One is blue, where the data is already sent and it is waiting for an acknowledgement. The moment they receive an acknowledgement, these will be emptied. The orange data that you see here are the data that are waiting to be sent across the TCP connection that is created between the sender and the receiver. And the white ones are the empty chambers where there is no data, right? The receiver side has just two chambers, meaning that this blue information that we see here, the blue data, right? The blue data that we see here is sent, right? And all that data is collected in the buffer of the receiver side, and it is waiting for the transport layer to send it to the application layer. The moment these data is processed, these chambers will get emptied, right? So it is very important to visualize the concept of buffer. It is very important to visualize the concept of window, right? Or the window size that we saw in the header of the TCP field, right? So consider this window as this chambers on the sender side and the receiver side. Okay. So in the next video, we will see how TCP treats segments, right? How TCP marks these segments, uh, and it gives it a sequence number, and how sequence number and acknowledgement number play an important role in communication. We will see this in the next video. I hope you liked this video. Please do comment for any question or any query, and I will be glad to answer it. Thank you and have a great day.